Hello, everybody. Welcome back to Making Records with Eric Valentine. That's me. You can see I'm in a different location, just trying to figure out how to make all this work. Let's see. Everything is now set up in the barn, so I don't really have my spot upstairs. That's back to being a bedroom. Sagan is asleep, so I can't be in a different building because if he wakes up, he'll be traumatized for life if I'm not here. So I'm in our dining room, and I have my little earbuds in here. So hopefully this sounds okay. Yeah, so I mean, the conversion is pretty much happening here. I'm happy to announce that we had an amazing rehearsal with the whole band in the barn. People got to stay in the rooms. We pulled all of that together, and it worked incredible. It was totally amazing. And then I freed up another room in the farmhouse. We had like 9 people staying here at this location for these rehearsals for band and crew and everybody. Now Grace is off playing shows, so I'm here in the house. Sagan's asleep. This is my opportunity to do something like this. I think I'm going to be able to squeak this in before he wakes up. So things are rolling along. The next step, now, obviously I had to take a break for a little bit. It got super intense because there's real deadlines. I have another deadline. The next one is setting up for the first like real proper recording using the control room and everything. So that's coming up in a little over a week now, just over a week. And I'm super close, like the rooms are set up, speakers are sounding great. I just have to go back and test all of the audio wiring again. A couple days ago, I fired up my RCA tube console. That's working, so happy about that. It survived its downtime. So yeah, this place is kind of functional. It's surreal. It's like it's taken so long to get to this moment. It really felt like I was just going to be building a studio for the rest of my life and not ever actually using it. So it was amazing to finally get there. So that's great. Very exciting. And so now I'd actually done, I recorded an episode for this before, and I scrapped it because it was just too disorganized. There's so much going on with this metal resonator panel thing, these VPR panels, that I didn't come close to really actually presenting it in an organized way. And I was missing some documents. I realized as I was talking through, I was like, oh man, I should show this too. So this time I really took my time, got stuff together. I've got like a little list of stuff to talk about in the right order. So this will all hopefully make sense. I can present this in an organized way. There's just a lot going on with this. And it happened over a kind of a long period of time of actually sort of conceptualizing it, getting the information, getting the materials, starting to build them, testing the materials, like doing this whole thing. It was a lot. So I think I can actually present this in a meaningful way now. So here we go. I know a lot of people have been asking about these, these panels right out of the gate. There was confusion on my part. It seemed like some confusion online about what these things actually are and what they're called. But I think I've finally really pinned it down. What I built is VPR panels. There are people that said that. You all are right. So VPR panel is what I built. And when I went back to the original document that Jürgen had sent me, it was this. Okay, I should just look at it here. It said right here, Verbundplatten resonator. Yeah, so it's definitely the VPR thing. And I'll show this document. I got all kinds of graphs and stuff to show. So here we go. We'll start with the Jürgen design. These are definitely the VPR things. This is the version where there's a piece of foam that's against the wall, and then a piece of metal that's suspended, and then another piece of foam in front of it for the ones that you want to be ultimately sort of absorptive in the sort of mids and highs. And the idea is that the piece of metal does not touch the front and back foam. It should be hanging, suspended in between them. and I got, this all started from Jürgen Strauss, the guy that made the speakers I'm using, and he sent me this document. So I thought I'll start there. This is the design document that he sent me. This is all in metric units. So for all you Europeans, you'll be happy to see that. Generally meaningless for me. I mean, I kind of have a general idea what it means, but not in a very detailed way, sadly. But here it is. And so you can see this is a side view of it. Here's the back panel, which is 100 millimeters, and which is roughly 4 inches for you Americans out there. And then you can see this blue strip here. That's the piece of metal, and then a front piece of foam, which is 40 millimeters, about 2 inches. And so those are the dimensions that I use for mine. I made mine as just 4 inches, 2 inches, and then the piece of metal is spec'd as being a 1 millimeter thickness in this document. Maybe it says it down here somewhere. And so, I had to figure out a standard or a fractional equivalent of that in inches, in what's available to buy here. So we'll get into that. That was a whole thing. So then you can see this is sort of front on the panel, and so there's these like large bolts that you have to secure to the wall, and then a hole in the foam and in the metal, and they show the hole for the bolt just going through the back foam and just going far enough to hang the metal on. And then the front foam, I guess the front foam is then held on by double-sided tape. That was the original design. So that's why there's this extra area around the metal panel. This is where you'd put the double-sided tape that holds on the front foam. So that was the original Jürgen design. So then I will now show you, ultimately, I did a CAD layout for what my design was. And so here is that. Okay, so this is the back foam, and so I did a similar thing. My dimensions ended up being 39 inches by 51 inches, and so each of those dimensions is larger by 3 inches than the dimensions of the actual sheet metal, and allowed the sheet metal to be exactly 3 feet by 4 feet. Was just an easy, convenient dimension to do, and the 4 feet was important because a lot of this stuff is being cut out of larger sheets, which is 4 feet by 8 feet. That's the size of the material that they're actually cutting these from. And when I had this thing just a little bit larger, it created a huge waste of the material and made the cost of the metal panels go way up. And so I shrunk the dimensions, so 48 by 36, and then they could cut 2 of these out of every 4 by 8 sheet. Made them substantially more affordable. And I have holes in all 4 corners here, and I'll show you what happened with that. But we'll start piecing this thing together. So next is the steel sheet. So there's the steel sheet, and you can see I put it 1.5 inches in from the edges, so it would really give me some clearance with the foam tape. So this is where the foam tape would go, and you'd have this like 1/2 inch gap around the thing. And so here are the threaded bolts that I used. And so here I'm gonna spin this thing so you can see a side view of it. And so this is a cool threaded bolt that you can get from McMaster Carr. I have a spreadsheet that shows all the stuff on this. I think it shows the part number in there. But this thing is 8 inches long, which is longer than it needed to be, so I needed to cut them down. And I cut them to a custom length, so the bolts would end up holding up the outer foam, and that ended up being really important ultimately. So here is now the front foam. Here's the metal sheet. Okay, so I originally designed this so the metal sheet would sit on the unthreaded part of the bolt, and then I got these plastic washers made that would, theoretically would center this sheet metal in between the foam and try and keep it so it's not touching either of the pieces of foam. Just, a little bit of spoiler here. This all changed once I actually started building these things, and you'll see why when we get there. They ended up being a lot easier to do than this fussy looking thing. But I ended up cutting off these bolts. You can see if I remove the bolt, I drilled out a core of the foam to this depth, so this foam could also hang on the bolt, and that ended up being really important. So there it is. So this was my design of this thing. Based on what was presented to me from Jurgen, and then through all of my experimentation and my experience just trying to build them and testing and seeing really what was really essential about this design that needed to be preserved and what didn't really need to have to be there, I was able to dispose of and do it a little easier. And so here is now the very first test that I had to do. So I needed to figure out what bolt was actually going to work to hold this thing, figure out how heavy the metal's going to be. The weight of the foam was really not a factor, because that would ultimately, it can get sort of, you can use spray adhesive and adhere it to the wall, so the bolts wouldn't really have to hold up that weight. The front foam is only 2 inches thick. It's not that heavy, but the metal plate did have some weight to it, and it's hanging, like 4 inches out from the wall. And the way I did my control room is these bolts are being mounted in 3/4 inch plywood. That's just not a lot of depth. If I was able to really sink this thing in a couple inches, I know for sure it would be able to hold. But potentially these are going to start to bend down because they're only in 3/4 inches of wood. So I needed to test a couple of bolt sizes to see what would really work and hold this thing up and stay straight. I did that. Here was the very first test to see if that would work. So this is the first sort of actual experiment in the process of trying to make these crazy new absorbers that I'm going to do, that Jurgen Strauss told me about. He sent me some drawings of how to do this. I've talked to him about it. I think I've actually got it figured out. So here's the issue. The sheet of metal, the size that it is, it's only 1 millimeter thickness, but the size that it is total, it's about 20 pounds. And so that means if I only have 2 of these things, each one of these is going to have to hold about 10 pounds. So this was the test. Can I have this big bolt sunk into only 3/4 of an inch of wood and have it be strong enough to hold this thing? So I have 10 pounds here, and I have 2 different size bolts. This is a 3/8 inch diameter bolt. And go like this. This is about 4 inches out. This is what it's going to be. Okay, yeah, it's definitely sagging a bit. Yeah, probably about a 16th inch of deflection there. And there may be a way to compensate for that. I might be able to put it at a slight upward angle, so by the time the weight is on there, then it ends up flat and perfectly horizontal. Okay, here's the bigger bolt. This is the 1/2 inch one. Let's see what happens here. Ooh, pretty solid. I don't think that's moving at all, really. The problem with this one is that I can't find washers. I have to use little washers on either side of the sheet of metal that try to keep it perfectly in between the 2 layers of foam, so it's not actually touching the foam. And I can't find washers that are 1 millimeter thickness with a 1/2 inch inside diameter. So I don't know. Yeah, we'll have to. I guess I have to keep looking because this definitely is going to work better. I think that's enough of a difference that I got to try and figure it out. So there it is. First step: absorber panels. Crazy absorber panels. Okay, so that was the first test. So it turned out, the 1/2 inch one, I felt much more confident about using the 1/2 inch bolt. It was way more solid. And if you can imagine, as I was really pursuing this thing of trying to get this thing to hang perfectly vertical, in between two pieces of foam with 1 millimeter of clearance on each side. That's not not easy to do. And it's like, if the wall that I'm mounting this on isn't perfectly straight, I mean, if it's going back even the tiniest bit and is not perfectly plumb, then and the foam is adhered to the wall, then the gravity will force the steel plate to hang vertical, and it'll touch at the bottom. It'll run into the foam. So there were so many issues with this. Just getting the bolts so they were mounted, the hole that I drilled in the wood, making sure that was perfectly perpendicular. There was a lot of interesting challenges with this, and I found a thing for that. It's a portable drill press that you can use with a cordless drill. So it has like a bracket and some springs, and you mount the drill in there, and you hold it flush up against the wall, and it makes sure that the drill is exactly 90 degrees, perpendicular to the surface of the wall, so you can really make sure you're going straight in and not just kind of like winging it. So I used that to drill all the holes, not only in the walls, but to do the foam core hole drilling into the melamine foam. So a bunch of challenges there, and ultimately I had to have those washers custom made. There's a company called Boker's that Undertone has used to make these little dust covers for our toggle switches, and so they can make washers out of pretty much any material with any dimension. So I did that. I had them custom made. Here's before you run out and have some custom washers made. I didn't need them. So you don't have to worry about that part of it. It's a complicated, stupid thing, anyways. So so there was that part of it. So the next step was getting the actual metal panels, and so I had to search around a bunch. I found a place. There were actually a few places that were willing to do it, but there was one place that was gave me the best quote, and they were just kind of great to deal with. Just simply called sheet metal design. They mostly make they form sheet metal into boxes and stuff for air conditioning systems, and so they don't typically make stuff like this. And that's one of the things that's really funny about this process is, like, all the people that you're communicating with along the way, they're like, wait, what are you doing? Like, what is this for? Everybody's just totally confused by it. It's like, I just need a metal panel with 4 holes in it, and that's it, and so, but yeah, so I was able to work with them to do this, and they were great. And so, so the first sheet metal panel, I kind of got the actual thickness wrong. And I think I explained that in this next clip, so you can see this. And so I wanted to actually test the resonance of this panel, because my understanding of it was that the metal panel should resonate at around 60 hertz. The description of this thing is that it'll absorb everything down to 60 hertz. Like the foam will absorb only down to sort of like the maybe low mid range, and then this metal panel sort of picks up where the foam can't absorb anymore, and the metal panel, the way it interacts with the foam behind it, then will absorb a bunch of lower frequencies beyond that. And if you get the resonance of the panel right and it pairs up properly with the front foam, then you just get this very uniform absorption all the way down to 60 hertz. So I was trying to make sure that the metal panel that I was going to have was going to resonate at 60 hertz, because first of all, it was not going to be exactly 1 millimeter. I couldn't buy it in that form here. And my dimensions were going to be a little bit different. My dimensions were a tiny bit smaller. And so here is the clip of me testing the metal panel for the first time. I came up with a way to try and test the resonance of the panel. You'll see all that. So here we go. Check it out. All right. So I've been waiting for this moment for a little while here. I finally got the prototype of the sheet of metal that I want to use for these custom-made absorbers, based on the information that was given to me from Jürgen Strauss, the guy that makes the speakers. And so there was a little bit of a misfire here. I learned something that gauges for sheet metal vary depending on the type of material. Doesn't make any sense to me. Like,
18 gauge sheet metal should be the same thickness regardless of whatever type of material it is. That's not how it works. So this sheet consequently is a little bit thicker than it's supposed to be. The design of this thing is supposed to have sheet metal that is exactly 1 millimeter or 0.039 inches. According to one gauge that I looked up on the internet, that would be gauge 18, but that was for brass or something else, and it wasn't for steel. And so the thing that I got is thicker than that. It's 0.047. Apparently that's really what, steel sheet metal 18 gauge is. So I screwed that up, but I've been wanting to do this experiment because, the concept of this absorber is that the sheet has a resonance at a low frequency. It sort of picks up where the absorptive material leaves off, because the absorptive material is not deep enough to be able to absorb energy way down there. And so the way they've designed this thing, the sheet is supposed to resonate around 60 hertz. And so 1 millimeter thickness at roughly this dimension right here. Let's see, can you see? Yeah, you can see this thing. It's about 4 feet by 3 feet, something like that. It's very close to the original design dimensions. I'm going to do some smaller ones, and in that case, I'm going to use even thinner sheet metal to get the frequency lower. I've seen lots of posts on the internet about this, and there seems to be some confusion about it. I was even a little confused about it, and Jurgen cleared it up for me, that the thicker the metal, the higher the resonant frequency. It's a little bit counterintuitive, and I saw people online saying, like, if there's more mass, then it should resonate at a lower frequency. That's not really the way it works. In this case, it's really the stiffness of the material that dominates, affecting the resonance. And so thinner material will allow greater excursion and will resonate at a lower frequency. So this is not ultimately the thickness that I'm going to use, but it's sort of a proof of concept. And so this should end up somewhere a little bit higher than 60 hertz, presumably, if all of these concepts are accurate. And so what I've set up here is the sheet of metal is suspended, and in this system, the sheet metal needs to be free, hanging free, not touching anything, with this type of absorber. I've seen people talking about VPR style absorbers. That apparently is a different thing, where the sheet metal is actually adhered to a layer of foam. This doesn't work that way. So I double checked. I asked twice about this with Jurgen just to be totally sure, and he's 100% sure. I trust him. The guy knows what he's doing. So he said definitely the sheet should not be touching any of the foam or anything like that. It just suspends free, sandwiched in between these two layers of foam. So here I have the sheet suspended, not touching anything, sort of precariously on a mic stand, and I got this little ball chain thing that you'd use to hold your keys or whatever. And so we'll be able to see how much it vibrates at different frequencies. And so I have it set at 60 hertz first, which was really the target frequency. And I'm going to turn this up really loud. I think ultimately if I post this video, I'm going to have to filter off the low end because it's loud in the room. I've been tinkering around with this. I have to have it pretty loud to really be able to see what's going on. Okay, so here we go. I'm going to turn up 60. So there it is. And let me see if I can turn this camera around. I'm going to turn the camera around so you can see. Okay, so now I can see what you'll be seeing. And my voice is going to sound weird because there's so much 60 hertz in the room. And so the idea is to be able to see how much that chain is bouncing around. Not a lot. Like if I look really close, and if I touch the panel, you can feel that the panel is vibrating a little bit, but not a huge amount. It's definitely resonating a little bit. So then there's 65. Still not a lot of movement there. Yeah, probably even less I feel even less vibration in the panel when I touch it. Okay, and there you go. So you can see that chain bouncing around on there because the panel is really resonating now. Look at that. It's moving a lot, and you might even be able to, see the panel itself vibrating. You see dust falling off the ceiling and stuff. It's really loud in here. But there it is, and when you put your hand on it, like it's wobbling like crazy. So there's the very clear resonance of the panel, and it makes sense based on what you're going to sing. Let's go even higher. Okay, and then there it is, and now it's not really bouncing around again. We went out of focus, but yeah, there we go. Let's go back to 70 one more time. And boom. Little bouncing chain. You can see it moving around. Vibrating. Yeah, it's pretty subtle on the camera, but it's quite obvious when you're standing in front of it, and really apparent when you put your hand on it. So that all adds up. This panel is definitely thicker than I intended it to be at 0.047 inches. And so, according to Jurgen, that would bring the resonant frequency up. It did. So this thing is clearly resonating at 70 hertz instead of 60 hertz. The target is 60. So I'm going to, I already, when I picked the thing up and realized that it was thicker than it needed to be, I told the fabricator, okay, I'm gonna have to do another one, at something that's thinner than this. So they're sourcing the material. I'll be able to do this test one more time and confirm that I get the resonance, in the right range. And then for the smaller panels, I'll do even thinner metal for that, and try and always keep it, the resonance of the panel down around 60. And depending on what happens in the room, if I really need to absorb something, lower than 60, if I have some significant problems down there, I could swap out these larger panels, with some thinner metal and bring that, that focus point of that low frequency absorption down lower, or, target it better at another frequency. So there we go. First experiment with these crazy custom made absorber things. So excited about this. I'm in the process of ordering the melamine foam and figuring all of that out and how to cut holes in it, and there's a whole thing. So I will keep you posted as it develops. Here we go.
All right, so there it was, the first test, even sadly with the wrong thickness. That really surprised me. So the test, it, at least I was able to confirm that the test setup seemed to be doing something meaningful. So then I went back to the sheet metal company, got something that was a lot closer. So I switched to, I believe, 20 gauge, which is a tiny bit thinner than 1 millimeter. I forget exactly what it is, maybe 0.0365 or something like that. And so, but I figured this is probably going to end up maybe in the right place, because my sheet was also just a tiny bit smaller in the dimensions than what was originally specified in Jurgen's document. So I was just hoping, like, tiny bit thinner, tiny bit smaller, maybe we'll end up in the right place. So here is the next round of testing when I got the next prototype of the sheet metal, and I was testing that. So this is now 20 gauge with the final dimensions being 4 feet by 3 feet. Here it is.
Okay, so it's round 2 here with the resonator sheet. Probably heard in the previous one, I got the thickness a little bit wrong. They were nice enough to do another prototype for me, and I did a little more digging around with the dimensions of the original design that I got from Jurgen, and so I could they didn't have like an exact match for the dimensions that I needed. So I needed to figure out if I should fudge a little thicker or a little bit thinner. And it turns out a little bit thinner. So my sheet is a little bit smaller than what the original design was, and so it makes sense to make it a little bit thinner. Hopefully we'll end up at 60 hertz. Today I've got my expert assistant, Sagan Potter Valentine, right there. He's dialing things in on the RCA console. He's got his oscilloscope there, checking stuff over there on the oscilloscope. Cool, yep, just making sure the screwdriver fits in the headphone jack. That's great. So here it is. I got the new sheet is set up here, and we're going to run the tones through it again. Last time, I started at 60, went up to 70, and realized that it was really resonating at 70 hertz. So I'm gonna go the other direction. We'll start at 70, go down to 60. Hopefully, because the dimensions are different, the thickness is a little different. I don't know if this is going to end up exactly at 60. We'll see what we get. So here we go. It's going to get loud in here, buddy. You're going to hear a bunch of low, hummy stuff. You ready for that? Okay. Okay, good. Here we go. Oh my God, it's going to be super crazy. Whoa. Okay, so here, this is 70 hertz. And I'm going to turn this around so I can see what you're saying. Okay, so there it is. We got a little bit of movement with the chain there. Not a huge amount. And it doesn't feel like it's really vibrating a whole lot at 70. So resonance is definitely no longer at 70 hertz. So we'll just start going down. There's 65. Yeah, maybe a little bit more. Yeah, I can feel a little more in there. And then okay, here's 60. Oh yeah. Oh yeah. Look at that. Wow. Okay. I think we got it. That thing is bouncing around like crazy. I mean, you can see the bottom of the sheet vibrating around. This seems even more dramatic than what we're seeing at 70 hertz on the thicker sheet. So yeah, this is spot on 60 hertz. Let me see. We'll fish around a little bit, see what else we get here. There's 59, and it definitely calmed down a little bit. 61, that seems probably closer to what it wants to be, but still, that's the thing. Wow, look at that. We got super lucky. The dimensions combined with the thinner material ended up putting me right at 60 hertz. That's good news. So this stuff is 20 gauge steel. So that is 0.0359 inches. A little bit less than the, it's like 3 thousandths less than 0.039, which is about a millimeter. But it looks like it all added up great. So we got our sheet. We're ready to do this. Okay, next I gotta get some melamine foam, figure out how to drill holes in foam, all that stuff. So onward, here we go.
Okay, so there it is. I was very excited about that. I felt like, okay, I'm I'm doing this right. Yay, this is going to work. And I should just add, and you could hear Sagan in the background there, always adorable. My trusty assistant. But when I discussed this more and tested it more, because I ended up getting sheets in other dimensions that were even thinner metal. I got ones that were 22 gauge, ones that were 24 gauge, all kinds of different stuff that I experimented with. And I started to realize that there are actually resonances at a lot of different frequencies. When I really started to experiment with this more, it really wasn't just one resonance, And And the other thing that's a factor is really the dimensions of it. So like the length versus the width. The length of the metal is going to also determine its relative stiffness. And so, that's a factor as well. And then, so there was a point where I was measuring all these panels endlessly over and over again, and I'm finding resonances all over the place, and I'm trying to figure out, like, oh my God, what is the real resonance? Did I really do this right? Is this wrong? I don't know what's going on. And I managed to get on a Zoom with Jurgen and just, discussed all of this with him. And he put my fears to rest and was like, this is all way more broadband than that. It doesn't have to be exactly 60 hertz. It doesn't work that way. And the plate that is anywhere near this thickness and anywhere close to these dimensions will work great. And it's very broadband, so it's really going to be, getting activated by all a range of frequencies down in there in that area, and it will work. And so again, it really didn't have to be as precise and fussy as I was originally, telling myself it was. And so that was sort of a relief to hear, and I was able to move forward, and not be obsessing over the resonance of this panel so much. And then I also went back and I thought, like, if this is really a big deal, then I checked to see what the thickness was on the ceiling panels that I'd gotten from the Renz company. This was a different type. I think you saw in the previous video with the ceiling panels that it turned out these were not VPR style. They were, the metal was actually glued to the foam or the insulation material they had in there, and so I was curious to see, like, I got 3 different sizes of these panels, and it was a huge difference between the smallest one and the biggest one, and I wanted to see if they were varying the thickness of the metal to accommodate the different size, to try and maintain a consistency with the resonance of the panel, and they were not. So they were all the same thickness. The metal was the same thickness on all of them. And so regardless of the size and the relative dimensions and all of that. So it really seems like, the thickness of the metal is probably the dominant issue. Jurgen did confirm that, like, if you have a panel that is, a somewhat significant amount smaller, then it's probably beneficial to make it a little thinner. So it will, shift the resonance to a lower area, and sort of keep you in that range. But it's not super fussy. So anything around here is going to be good. And later I did some experiments, because I had all these panels at different thicknesses, and I experimented a little bit with, the different thicknesses that I had to see which was more effective. And I think ultimately thinner was better in the dimensions that I was using. This was sort of a mid-sized panel that I was testing, because I had, like, I think I had a 20, a 22, and a 24. And it looked like ultimately the 24 was, this stuff gets so complicated, but it was having the greatest effect on the issue that I was testing for. So there's probably more exploration to be done there, but there was a certain point where I'd ordered, like, whatever it was, I don't know, 14 of these panels, at $100 a piece, at the 20 gauge thickness. The difference was not substantially different, and so so I just stuck with it and move forward. So there you go. There's the deal with the metal panels. If you can find a place that can make them, it's not really that complicated. If you can find something that can just cut out a sheet, 3 by 4 feet, put a couple holes in it, good to go. The other thing I should mention, like all these all these drawings and design files show 4 holes in there. And ultimately, I only needed 2 holes to actually mount it. It was convenient to have 4 holes, because then I could mount it either vertically or horizontally. And so just being able to fit these in all the different spaces that I needed them, it was nice to have the 4 holes for that. But I never actually used all 4 holes in any of the hangings of them, just, so you know. So now I have a video of us actually putting one of these together. So Alex was helping me again for this. He was around for this whole period of just doing this acoustic treatment of the control room. And so we recorded the whole process. So you can see my like portable drill press thing. You can see us core drilling the foam. You can just see the whole process of putting one together and getting it on the wall. So here is that video.
Okay, so I think we've got this process dialed in enough that we're brave enough to videotape it. So, in theory, we won't totally screw this up this time. So this is the process of assembling these wall absorber thingamajigs for anybody that might want to take on trying to build these things. And so, so on the wall, we already did the measurements for the wall and got the bolts mounted in the wall. This is going to be the top middle one. And so the first thing we do is get this piece of metal centered as good as possible in the foam piece. The piece of metal is supposed to be 1.5 inches in all the way around. So originally the idea was to have 1 inch wide double-sided foam tape going around the perimeter, and that would glue the two pieces of foam together or tape them together. But with experimentation, we have discovered that the tape is not necessary. It's actually better without it. Okay, so I should help with this so we can get this centered. Okay, so then we got to drill 1/2 inch holes in the foam, and that was a question that I had at the beginning of this, like how do you drill a hole in foam? And this is how you do it. It's this foam core drill bit thing, and it works amazing. I found it on Amazon, and it's for making furniture. So just get a little delightful little boop. Okay, so take the sheet off. We're going to put up the back foam. Okay, so now we'll do the front piece. We have to use the piece of metal as a guide to drill the foam holes. For this one, it's a blind hole, so you don't want to go all the way through, because then you'd see the end of the bolts on the outside of the thing. And these all ultimately are probably going to get covered with something a little prettier. But yeah, so I put a mark on the drill, and after you do the 4-inch ones, when it goes all the way through, it erases the mark, because
this stuff is like a magic eraser.
like exactly, melamine foam is a magic eraser. And also got this portable drill press thing to make sure that I'm drilling these holes super straight. This is also Amazon. I don't know what it was, about 40 or 50 bucks. Yeah, so it turns out that the bolts, they're threaded on the end, and I was originally planning on having the plate sit on the unthreaded part of the bolt. The plate was too close to the back foam, and it was making contact with it. And with this design, it's really not supposed to do that. And so there's a lot of debate about that, and I'm sure I'll cover it in another thing. But so it turned out that the threads are a really great way where you can incrementally sort of adjust it and lock the plate into a place where it won't move around. I was originally going to use washers to try and create this 1 millimeter space on either side of the plate. The tolerances are not even near tight enough to be able to keep that metal plate suspended between the foam with only a millimeter gap and not have it make contact. The metal plate isn't straight enough, the wall's not straight, nothing is straight enough to be able to do that. And so it turns out it doesn't really have to be that close, but it is beneficial to not have the metal touching the foam. We did a bunch of tests where we had it all, together really tight, and we spread it out a little bit, and it seems like you get more of the low frequency absorption benefit when they are not actually physically in contact. So, there's a lot of different opinions about how to approach this type of absorber on the internet, and at least with our testing, the no contact version is the way to go. And so you can put it on here and just kind of sight through it with the accuracy and straightness of the plate. We can do about a 1/4 inch gap on either side, and we can adjust it. And you just adjust it until until you still want to see light through there, so it's not fully in contact. The foam is not fully in contact with the metal plate. And I'm sure I'll have another little bit where I show all the graphs of the results of this, but these things really work. They are freaking cool. So
Another test.
It's time to do another test. Let's do it.
Okay, so there it was. It's kind of a long video, but you really get to see that the whole process of putting one of these things together. It really wasn't that hard at all. Ours was a little bit fussier because the holes that were drilled in the sheet metal were not extraordinarily precise. The positioning of it, this sheet metal design place, they're used to working with kind of rougher tolerances than some other applications of this kind of thing, and so they just build these metal boxes, for air conditioning, so just to make sure everything was going to line up perfectly. For every single sheet, we would take the actual sheet that was being paired with that piece of foam, lay it on there, and use it as a guide to drill the holes. So I knew all the holes would line up on the foam and the sheet, and everything would line up precisely. But if you have somebody that can place all the holes in the sheet very accurately, you could just have one template and then just drill all the foam, do it more assembly line style. It would probably go a lot faster than what we were doing. But I wanted to get it so there was pieces of foam that were paired up with the pieces of sheet metal because the holes were not exactly perfectly placed 1 inch in from each of the corners. So there you go. We got a bunch of them up, but as we were putting them up, I was testing a bunch along the way, and so I had this issue with. And I'll talk about this a little bit in the next video clip. When you put a speaker in a room, near a wall, presumably the front wall of your control room, and I've experienced this thing where there's always this one cancellation right around 100 hertz or just above that, and so it was a great way to test to see if this style of thing is going to really be able to affect that, because it's supposed to absorb everything down to 60 hertz. It's right, in the range where this was going to be, and see if this is really going to have an impact on that. So we set up a test specifically for that, because I put up a speaker in the room. There it was again, that same cancellation, right up around 100 hertz. Drives me nuts. I had to deal with that in the Topanga Ice control room, and ultimately, ended up having to deal with it here. And so check this out. This was very, very interesting result. So here it is testing a speaker just in front of the wall, and we're able to just put up, there's basically nothing on the wall, and then put one of these panels up to see how it performs. Check it out. So we are getting into the nitty gritty of this homemade absorber thing, and we finally got some tangible results. So we just did a little test setup. This wall had nothing on it, and this is about the distance that I'm going to be sitting in the room
we just place the speaker in a spot, and that's close to where it would be. And the same thing showed up for this that I've seen a lot. Pretty much every room I've been in has this cancellation around 100 hertz, maybe there or just above, depending on how far the speaker is from the wall. And so we put the speaker in with nothing there, and there it was again. That same cancellation has been driving me nuts. And so it appears that it really is off the back wall. And you can move the speaker away and the frequency lowers. You move the speaker closer to the wall, the cancellation gets higher. It seems like it's, predominantly, an interaction between the speaker and the wall behind it. Obviously, these things are super complex. There's reflections going in all directions. And so it can, add up in different ways. There are probably other influences involved, the dimensions in the room, all that. But the back wall seems to be the overriding issue. So then we were able to see, like, okay, these absorbers are supposed to, with only a 6.5-inch depth, get you basically like 100% absorption. They refer to it as open window type absorptions, as if there's a hole in the wall, all the way down to 60 hertz. That's the claim. And so finally, I'm able to try and test this to see if it's going to do it, because up around 100 hertz, it should definitely be addressing that frequency range for sure. And so what we did is we started off without the thing on the wall at all. So just a bare wall behind the speaker. And, the cancellation right here, I'm just going to do sort of a crude version of this. I'll probably do a whole other thing where I actually pull these up and I can do a screen capture so we can see it in more detail.
So here is the first graph, nothing on the wall at all. And so you can see this cancellation, it's right now it's sort of zeroing out at around, so the average is around -10. This thing is at, the peak of this is like -32. That's a, 22 dB, cancellation at whatever this is, 124 hertz. That is an absolute disaster. And so here it is now. We'll add in with the 4 inches of foam. And you can just see, like, this is not making a difference that's going to matter at all. I mean, it goes from, a 22 dB cancellation to a 21 dB cancellation. This is not a bass trap with 4 inches of foam. It's just, yeah. Okay. So now here it is with adding just the metal, just adding the metal on top of that foam. And look what happens. I mean, that is just a dramatic change here all of a sudden. So now we'll look at just these two. And so it went from -32 now to whatever this is, -24. So that's like an 8 dB difference there. Okay, so now we added the whole panel. So this is now the back foam, the piece of metal, and the front foam. And then you can see it gets even, a little more than another dB of absorption there. And so now when you compare to the original, this is the difference that we're talking about that it's making. And so again, this is like -32. Now we're up close to -22. So it's almost a 10 dB reduction in this cancellation with just one of these panels placed behind the speaker. And so, I know I'm sort of repeating myself, but I've just never seen, a 6-inch absorber do anything remotely like this. I think that is an incredible result. So, and then, I think, as I said, here it is. We did the test where we collapsed everything together. I just want to confirm for myself, it really is better to have this thing floating in between. And it definitely was. So here's that difference. So this red line, this is with everything pushed together. This is with, a gap between the foam and the sheet of metal on either side. And you can see the difference of the performance there in this range. The reduction in cancellation, is probably an extra, whatever it is, 2.5 dB, of it performing better, with the pieces separated. So there you have it. That was enough confirmation for me to know that, okay, this approach is working. Then from here, we just started adding more and more panels. And this is a really interesting part of the process. My sort of naive assumption was that every time we add another panel, it's just going to start looking better and better and better. It's going to get flatter and flatter, the whole time. And that is not how it works. I'm going to keep saying this over and over again. Like, the room acoustics are so complex. The sound is just emanating in all directions and reflecting off of all of these, 6 surfaces at different timings in different directions in all these different ways. It's extremely complex. And so the other thing that's really important to understand is that when these cancellations happen, it's because, generally, I'm more concerned about the cancellations than the peaks. The peaks, generally, especially in the low end, tend to not be as problematic for me. They're not as dramatic overall, I've found, and typically, the way I voice a room, there's usually a rise in the low end, and so the way I'm sort of, looking at tuning the room is dealing with more of the cancellations than the peaks, because I'm trying to have a little extra low end down there anyways, and so the peaks end up not being as much of a problem, as long as it really isn't, like one frequency poking out. But yeah, and so that's why I'm really focused on the cancellations. And so what's happening when there's a cancellation is that, there is a reflection in the room that's coming back to your listening position, at a timing and a phasing that's causing a cancellation with another reflection in some other direction, or with, the sound emanating from the speaker. And so it can be happening in all these different ways, but it's a collision of frequencies that are reversed in phase that's causing a cancellation at a particular frequency. And so you can be in a position, so like, I'm sure, as many of you know, that, when you're canceling frequencies, so if you have, a frequency that is, 2 frequencies that are, or 2 signals, I should say, that are opposite polarity, and you start blending them together, when they're the identical volume, it will completely cancel out. But as soon as you change the volume of any one of those in either direction, then the cancellation is not as severe. And so you can have situations in the room where you probably have two signals that are reflecting back into this position that are causing a cancellation. You add an absorber, and maybe what it does is it's absorbing more signal of one of these that was actually a little louder than the other. And so now it's actually being brought closer to a more equal volume, so the cancellation becomes more severe. So you can add a panel and a cancellation will get worse when you graph it, which can be very, very confusing in the process. And so I was sort of driving myself crazy along the way, like adding a panel, like, oh, maybe I shouldn't add this one. Oh my God, it's making it worse. Oh no. But it was just a moment along the way where, it happened to add up in a way where the signals that were causing the cancellation were getting equaled out more, I think. But again, it's so complex that it's really hard to know. And, at a certain point, I just sort of accepted the reality, like, listen, I want more just uniform absorption around this whole room. I should just put them all up and stop worrying about every single panel I put up and testing it to see if it's making it better or worse, because I know I'm going to want absorption everywhere. I really don't, you could end up in a place in your listening position where just by sheer chance, the room has longer sort of reflection time in the room, and there are resonances in the room, but they happen to add up in the way in your listening position that is reasonably flat, but the rest of the room will be much more anomalous. And so there'll be all kinds of variations in the response as you move around the room. The more you reduce these reflections in the room, the more uniform the room gets. And so that's really where I was headed. It's, I really want the room to be, if possible, pretty much totally anechoic in the low frequencies, and have as you get into the higher frequencies, have some more reflections in the room, so it doesn't feel like you're in a vacuum. That's my goal. And so I stopped driving myself crazy with that, and just at a certain point, I'm just gonna put them all up. But here is here's the crazy part as I was doing it. So then I moved the speaker, because I had the speaker just in the center of the front wall. So I moved the speaker to the left position. So that's why it says left means left speaker position. And this was at the point where I had the front and back walls all completely covered with these VPR absorbers. And so then I added, now this was now with half of the left wall. And I was expecting a huge improvement, and it got worse, a lot worse. And so you can see this same pesky, cancellation, which clearly now is not just an interaction between the speaker and the back wall, but it's like the back wall and the side wall and probably the floor. All those things are influencing it. And so, my ultimate plan was just like, let's reduce everything and try and get the whole room to be a little more uniform, and then figure it out from there. Okay, and so then let's see what's next here. I did another test where I put the speaker in front of the sidewall, because that didn't have a bunch of panels on it, and I could sort of, do another round of testing a specific, just the effectiveness of the panel itself. And this I was comparing gauges of metal. And so here is the difference between what was 24 gauge and 22 gauge. And it looked like with this size panel, because this was a smaller size panel, the 24 gauge was a little bit more effective. At this point, I had already committed to using the 22 gauge, because in my previous testing of just testing the resonance of the panels, getting me closer to a 60 hertz resonance, that's what I was focused on at the time. But it is possible that 24 gauge in this dimension might have actually performed better. I think, the amount that you can chase this, it kind of goes on forever without, I think you could probably get to an answer quicker if you had a real like acoustic test facility. They have these rooms that they use for testing of absorptive panels. I don't know if you've ever seen one of these, but it's crazy looking. It's basically a reverb chamber, and the way they evaluate this is the reduction in reverb time at the various frequencies when you put a panel in the room, and then they can really measure how much a panel is really affecting what frequency ranges. And so it's this big, huge reverb chamber, and they have this big, huge like sail that spins around and moves the air around in the room for some reason, I guess to reduce standing waves or something. I don't know. It's wild. But yeah, so you could probably get to the answers very quickly if you were in a test facility like that, but they're hard to find and expensive. So I'm on my own journey here. Okay, so then let's see what's next. So this is left side close to back wall full treatment. Okay, yeah. So I think I put the speaker on the back side of the room just to try and see if it was substantially different there, and it wasn't. The same kind of issues going on. My room is pretty. It's just a rectangle, so it was probably going to be similar in all these different directions. Okay, so then what is this? Okay, so then I did a comparison of the whole room either being, with everything sandwiched tight together or being loose, because it was pretty easy to adjust that in the room at this point. And this is all with just this little Atom, T8V or something speaker, because I could just move it around easily and experiment with it. So at this point, the speaker is in the center position in the front of the room, and we have all of the panels up at this point. So front wall, back wall, left and right walls, the ceiling. There's nothing on the floor. There's no carpet or anything on the floor. That wouldn't really affect the low end anyways. And so I just wanted to see, like, throughout the whole room, because I saw a difference when I had the one panel between being loose and tight. Was it going to really make a difference throughout the whole room? So this is what the room is looking like, with all of the foam and the metal panel not touching each other. And then here it is with the whole room and the foam all sandwiched tight together. And at least at this one pesky frequency range, this whatever it is, 120 hertz ish, it was more of a problem when everything was pushed together. So further confirmation that it seems, this VPR style where they're spread apart definitely seems to improve the performance of them. So this is a good time, for anybody that wants to chase this thing. I have a spreadsheet so you can see what it cost here. So let me pull that up. I made sort of a bill of materials as I was working on this. And this will be an opportunity to talk about yet another experiment that I did. Okay, so here's the spreadsheet. I crossed out the double-sided tape because I realized you don't need that. These things are definitely performing great without it. And in reality, like, there is no way I was going to be able to get the tolerances tight enough to have that piece of metal hang in between two pieces of foam on a wall with 1 millimeter of clearance on each side and have that plate not actually touch the foam. That was not going to happen. There's no way it was going to happen. So fortunately, not necessary. And so that also meant that the washers, I didn't need the washers, so I crossed those out. Okay, so here's the threaded metal studs that have like wood threads, like a wood screw threads on one side and machine threads on the other side. And the machine threads, I think I talk about this in the video, those are really handy because you could actually use them as sort of a way to, force the metal to hang in a particular position. And so I cut everything to make it work that way. And we, sunk the studs into the wall so it would place the metal sheet just right on the threaded machine parts. And so you could use those as a guide to just, sink the metal into a place on those threads where put a perfect little gap between it and the foam. They're very handy to have in that way, so the metal wasn't sort of sliding around on a smooth surface. Those things were kind of annoyingly expensive, $8, 50 cents a piece. And fortunately, originally I was thinking I was going to potentially need 4 of them, which was going to get very expensive, like $35 with these stupid, metal, wall anchor things. But only 2 of them, $17, not too bad. So here's the piece of sheet metal. Those, it varied on the size a little bit, but they were all roughly around $100 for me. It's going to vary on whatever fabricator you find in your area if you're going to go after this. There was one person that was quoting $200 a sheet. So hopefully you can find somebody that'll make these things affordably. Man, the melamine foam, that stuff is expensive here in the United States. It's made in Europe, and I think that's why Jurgen recommends using it. I think it's probably way, way more affordable in Europe than it is here. But that was the most expensive part of this, was getting the melamine foam, which, by the way, is the exact material used for a magic eraser. And so you basically are covering your wall with these 3x4 foot magic erasers. But it's really expensive here, and I had a slip of the brain when I was ordering it. I went through the same process of changing the dimensions to try and get it to a place where there would be as little waste as possible. And when I placed that final order, I went with the wrong dimension in a particular direction when I laid it out for this company that I bought it from. What were they called? This company, Acoustical Surfaces Inc. And so the largest pieces ended up being more expensive than they should be. But at the end of the day, the cost for the 4-inch piece and the 2-inch piece is probably going to be around $400. It's probably around $250 to $300 for the 4-inch piece and $150 to $100 for the 2-inch piece, something like that. And so it's about $400 for the foam, for the melamine. It was the only place that I could find in the States that would actually just cut the sizes for me and ship it to me. So annoyingly expensive there. Definitely the most expensive part of this. So then I tried another thing. Okay, so I don't have any video of this. It was just another sort of passing crazy moment along the way. And part of this was inspired by a comment that came in from one of y'all on YouTube. Somebody said that that the quarter waveform rule applies as well to these sheet metal absorber things. And so I was like, no shit. Okay, well, I was having these issues with these really low frequencies between the front and the back room. And so, I had a series of these 3 foot by 4 foot things. And so I decided, screw it, let me just try making a bunch of ones that are like 8 feet, by 4 feet, make huge panels of this and see if they'll actually really start reaching down to these very low frequencies that I needed to absorb on the length of the room to try and deal with like a 50 hertz cancellation that I had. And we'll get into that more in the next round of this. But and so I actually built 4 foot by 8 foot versions of these on the back wall and put them on the back wall. And I ended up using mattress foam for that. And so with just here you go. Here was the result. Made no difference at all. It didn't perform any better than the other one. And I even went through the process of recreating the 3 foot by 4 foot one with mattress foam instead of the melamine foam to make sure that it was still doing the same thing as the melamine foam. And it did. So I created the same test setup where I had the one speaker in front of the wall, was canceling around 100 hertz. I did the whole setup with the melamine and then swapped everything out with mattress foam. And it's this Y33 foam. I got it from foamorder.com. And the results were the same. There really wasn't any difference between the melamine and just using regular old mattress foam. So potentially, it's not essential to use this really expensive melamine foam when you're building these things, and you could potentially save some money there. The one thing to know is that the melamine foam is nice to work with because it has a stiffness to it. If you've ever held a magic eraser, it's the same material as that. And so when I was using the core drill to drill out the 1/2-inch holes in the foam, it was really easy to do on the melamine. And when I had this mattress foam, which is a lot spongier, it was very difficult to drill. And it was much trickier to hang on the wall because it was just kind of rubbery and it would sag and whatever. So there were some problems there. You'd probably have to build at least some sort of cleat to put under it to support it from the bottom, so the whole thing isn't just kind of sagging down. But it does work. So if you want to save some money, and so I bought these really large pieces of mattress foam that I could cut into smaller chunks, and then the total cost for the foam was more like $300 per panel, something like that. And then I found yet another thing on this foamorder.com. For some reason, I didn't find this when I originally was chasing this down. They had a section on there for acoustic foam. So, just full disclosure, I haven't actually tested this yet, but you can buy pre-cut pieces of acoustic foam from this foamorder.com of this stuff that's just like regular packing foam. And I'd have to actually get some of this to make sure that it would actually work, because any foam that you're going to use for this has to be open cell. It can't be closed cell foam because the air has to be able to pass through it. And so I'd have to confirm that this is actually open cell. But if it is, and if it's like some of the other acoustic foam that I've seen, I think this could work just as well, and it's super affordable. So then, the total cost for foam would come down to, like whatever. The 2 panels, the 4-inch and the 2-inch panels, it was like $78 and $40. So this is definitely something I'm going to do. I'm going to order some of this and see if it would actually work as well, because then, your total cost for one of these panels is like $250. Like that's very, very affordable for, there are people out there that are making this stuff, making these panels. I forget who all is doing it, but they're really expensive. They're like $800 to $1,000, a piece. So at some point when I have some time, I am going to test this. I have a whole other room that I need to do. I'm probably going to use the same approach in the small sound room, and that'll be the time when I can try this other foam, because I haven't even started doing the acoustic treatment in there. I can try that stuff and see if we can really get the cost of these things down to like $250 a piece. Man, that is a huge benefit. To be able to do these panels at that price point would be incredible. So fingers crossed that stuff works. Yeah, so there's the price breakdown. I think even with the melamine, it's definitely cheaper than the stuff that you can buy off the shelf. And you might be able to find a source for the melamine that's better than what I came up with. But that's really what's driving the cost of this thing. Then finally, towards the end of this whole part of the process, we brought in the Strauss monitor. So that's the next thing that we get to see, which is kind of fun. So this was the where I left off with the little Atom speaker. And then here is the Strauss monitor, and like, dun, 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 look at that. It's like a whole other octave of low end coming off that speaker, man. These things are so incredible sounding. Okay, so what is this? Let's look at this. Yeah, so this is like, way down at 26 hertz. It's peaking. And then here, this is the other speaker. Yeah, it's, like 40. Yeah, so it's almost an octave lower. The actual peak of the low end. But, still, if you're looking at, the way I ended up voicing the room and the placement of the speaker, everything is sort of hanging out. If it's probably sort of averages around -8. And so by the time you're at -8, it's still flat way down at like 22 hertz with that monitor, no sub, just the Strauss monitor. So I started playing with the position of the speaker in the room. So that became sort of significant at this point. I wanted to have the right, stereo width in the room. I find in the past, like if I get the speakers too wide, they lose their punch a little bit. And so I was just playing with the width of the speakers in the room and how close they were to the back wall to see if there's any benefit to pulling them off the back wall. So you can see what happened with that. So this is 25 inches from the side wall. I tried moving even closer to the side wall. The graph changed, and I think ultimately it got a little too wide. I had an earlier thing. I didn't save the graph of it for some reason, where they were even closer together, and it didn't feel right. It just didn't feel big enough in the room. And so 20 inches was a little too wide, so I went back to 25. This is where we were. And so there's the right speaker, there's the left speaker. And so here's the thing that's kind of interesting. I'm going to pull up Room EQ Wizard. And so this has the dimensions of my room loaded into it in the room simulator. And so with sort of a moderate amount of absorption, sort of like absorbing half of the energy everywhere in the room. And so here's just the left speaker. I put my head in roughly the same listening position. I put it at the height that I have. There's no crossover, but yeah, it's a ported speaker, and so then you can see the response here. This only goes up to 300 hertz, just so you know it's sort of the range that we're looking at. But here's a cancellation at 50. Here's a cancellation around 84, and then here's a cancellation around 100. And so when you look at this graph, here's 50. Here's 80, and here's 100. So like, it's amazing how accurate this room simulation was. I think having the rectangular room was really a benefit, at least when you're trying to simulate what you're going to get out of it. The room simulators are really very much more able to do an accurate prediction of the room when it's just square dimensions. And so this ended up being quite useful along the way. So there's another cancellation up here to 20 something, and I guess that's yeah. So here's that one. It's showing up right here. Dun, 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 to 215. So so very very informative. That Room EQ Wizard thing really translated to what I was measuring in the room. And I don't know how precisely I was able to recreate the positioning of where the microphone was and all of that stuff. I haven't really double checked that, but I'm guessing if I really took the time to make that exactly the same, it would really, really show up very, very similar. Because everything has a huge influence on this. Like the height of that you're positioning the mic, the distance from the speaker, the position of the speaker in the room, it all has a dramatic effect on the response that you get. So here it is, at the end of this part of it, putting up all these panels in the room that, as I was sort of told, was that it was going to, absorb everything down to 60 hertz, and still I've got some serious problems to deal with here. So here it is. It's probably averaging out, somewhere just around -10 on this graph. This thing, the cancellation is going all the way down to like -22. It's like a good at least 10 dB. It looks like, yeah, probably more than that. This is probably like 12, 13 dB cancellation here at 100 hertz, and again here at 50 hertz. These are big problems. I'm not done with this process, and so as I discussed it more with Jürgen, and even early on, he always said the same thing, and he has like all of this incredible analytic stuff at his disposal. He has these incredible, powerful supercomputers and all this stuff. He built this whole like audio laboratory in Switzerland that at some point I'm going to go and visit. But it's insane. He built this room. It's built by robots with clay bricks that looks like, I don't know, like a giant flower petal or something. It's so crazy looking, but it's supposed to be, in theory, the most acoustically perfect room or something. It looks insane and awesome and incredible, and I'm dying to go and experience it. So he's like, at this insane level of what he's doing out there. But even with all of that at his disposal, he told me like all rooms you end up in the same place. And he uses basically this approach. He puts up these VPR panels everywhere, see where you're at with the low end, and then you have to fix the low end from there. And so for him, it's like, Helmholtz resonators, things that are more targeting specific low frequencies to clean up the low end, and that's just how you do it. There's a certain point where the computers just can't really predict it that accurately, and there, the room is going to have a resonance down there, and you're just going to have to deal with it. And so that is going to be the next phase of this. So here I am. I've built all my VPR panels. I put them on 5 surfaces of this room. Sadly, I can't put them on the floor. And I still got some serious fucking problems here that I got to deal with. And so the next episode is going to be me dealing with that and actually getting to the end of the rainbow and getting that room totally sounding the way I want it. So I will see you then, and you'll see how that all happens. All right. Thanks for watching. See you later. Bye.